In this blue reel number 1, we discuss the real Schrödinger operator. I am Daniel Crespin. The real Schrödinger operator is the usual self-adjoint Schrödinger energy operator restricted to act on real-valued wave functions. The imaginary unit is dismissed. In this reel, it can be deduced from classical physics without using quantum axioms. This is a conceptually important initial step to obtain a deterministic time-dependent equation. Start with the classical representation of the bound physical electron by means of a real-valued wave function ρ equal to the product of the electron elementary charge and a positive wave function gamma plus having integral 1. The wave function gamma plus is the geometric shape of the electron. Wave functions will be assumed real analytic. An electron is a square if its shape is a square. A shape is a square whenever equal to the square of some wave function, and then the wave function is a root. The roots are integrable, belong to the unit sphere of the L2 norm, and can be traced back to Schrödinger under the guise of a squared modulus. Real analytic implies that the duppleton of roots is uniquely determined by the squared electron. Such duppleton is an element of the real projective space associated to the unit sphere. For a squared shape, the gradient is the duppleton of gradients. The internal momentum is the duppleton of the internal momentums. The internal energy is the square of the internal momentum divided by twice the electron mass. The gradient, internal momentum, and internal energy are functions of the root. The gradient, a geometric and also an analytic notion, is independent of the electron charge, mass, and Planck constant. The internal momentum depends on Planck constant, but is independent of the charge and the mass. The internal energy depends on Planck constant and the mass, but is independent of the charge. For a squared electron, the internal energy is defined as the internal energy of the shape. Integration by parts expresses the internal energy in terms of the Laplacian of the root. The term kinetic energy will not be used on the root and remains reserved for photons, these being the conjugate variables of the root duple. For a proton fixed at the origin, there is an electron-proton interaction potential. The electrostatic interaction energy of a squared electron is expressible in terms of the interaction potential, the root, and the L2 inner product. Again, for a squared electron, the total energy is defined as the sum of the internal and interaction energies. This total energy is expressible in terms of the root of the Schrödinger real operator and of the L2 inner product. The real operator H is therefore attainable within classical physics. Summing up, H is the linear operator having its associated quadratic functional equal to the classical total energy of a bound squared electron. Quantum principles have not been invoked. In a forthcoming blue reel, it will be proved using Lagrange multipliers and without quantum axioms that the stationary energies and stationary states of the bound electron are respectively equal to the eigenvalues and to the squares of the normalized eigenfunctions multiplied by the elementary charge. For additional details, see Schrödinger energy operator is classical. Motivations are discussed in Deconstruction of Quantum Wave Mechanics.